manipulator Jacobian. Right, so we were talking about how to track the velocity of the end effector and vice versa. So basically, when you have a manipulator like this, right? So this is your point of the end effector P, and these are the joint variables θ1, θ2, θ3. That's it. Okay. Now, if I want to, we did inverse and forward kinematics, so we know how the position relates. Okay, how the position, how these values relate to the x, y, and z, right, and also the orientation. We did this with forward and inverse kinematics, which is the relation between P and Q, back and forth, right? P is the point in three-dimensional space, and Q is your joint angle. Now we want to move on to tracking the velocity. Okay, velocity of the end effector. Normally, for a manipulator that has both, 6 degrees of freedom, so we track both the position and the orientation. We'll write it as x, y, z, phi, theta, and psi, right? Because these are the rates of change, we'll write it as a dot. Okay, because this is the rate of change, we'll write it as a dot. Okay, so eta is your end effector velocities. Similarly, we'll write Q dot. Q dot is nothing but rate of change of joint angles. So θ1, θ2, θ3 dot, up till θn dot. Right? So we want a relation between theta, which is your end effector velocity, and this is joint velocity. Now, one of these can be a prismatic joint. So if it's a prismatic joint, obviously, let's say this is a prismatic joint, you'll have d3 dot, okay? Because it is a link that is moving. So in this case, if you have a revolute joint, this theta is moving at some rate. Let's say this joint moves here. So it's moving at θ1 dot, rates per second. When it moves, this point is also going to move automatically. The manipulator is going to move like this. So P will come to P dash, or whatever, at this way. So we want to know that if I want to move from A to B, how fast should I change the joint angles so that the end effector can move at a given rate. To do this relation, we want to find a relation between eta, forward and inverse, and Q dot. This is the relation that we want to find. We want to find a relation between eta and Q dot. So we'll start with a very simple manipulator, and then we'll develop a very generalized approach that can be used for all manipulators. So as we always do, let's start with the simplest case where you have a 2 degrees of freedom manipulator, right? A1, A2, this is your P, θ1, θ2. All right? Now, in this case, we know the forward kinematics. Okay, so here eta, what will be eta? Eta will be equal to, we are only tracking the position here, x dot, y dot. Q dot will be equal to, you have two joint angles, so θ1 dot and θ2 dot. So, if x and y are known, I should be, x dot, y dot are known, I should be able to find theta dot, θ2 dot, or if this is known, I should be able to tell what is this, okay? So we have to be able to move back and forth with velocity parameters, just like we did with positioning of the arm. Okay, so let's take the forward case here. We know the forward kinematics, which is x is equals to a1 cos θ1 plus a2. Cos θ2. All right, y will be equal to a1 Now if I want to find the rate of change, eta, in this case, I'll differentiate this x dot will be dx by dt with respect to time. So this will be equal to minus a1 sine theta 1 times d theta 1 by dt, okay, and minus here a2 sine theta 1 plus theta 2 d theta 1 by dt, and then I'll have minus a2 alright, theta 1, theta 2. Same thing will, so this expression I can actually write it as x dot is equals to minus a1 sine theta 1. This will be theta 1 dot, okay. I can take sine theta 1, theta 2 common. Same thing applies to y. When we go to y dot, that will be equal to dy by dt. This will be equal to a1 cos theta 1 d theta 1 by dt plus a2 cos theta 1 plus theta 2 d theta 1 by dt. So I can write this as y dot is equals to a1 cos theta 1 times theta 1 dot plus a2 cos theta 1 plus theta 2 times theta 1 dot plus theta 2 dot. So if we concise these two expressions, we can write this as follows. We can write this as x dot y dot, or let me write it like this. If you see theta 1 is common here, theta 1 dot is common here and here. So I'll write this as a1 cos theta 1, I'm sorry, theta 1 dot minus a2 sine theta 1 plus theta 2 dot times theta 2 dot. Okay, there is a theta 2 dot. Let's go here. Y dot will be equal to plus a2 cos theta 1 plus theta 2 times theta 2. So I can write this in a matrix form as a relation between the two, which is, let's say, x dot y dot is equal to a1 sine theta 1 minus a2 sine theta 1 2. Here I'll have a2 sine 1 2, a1 cos 1 plus a2 cos 1 2, and here you'll have a2 cos 1 2, and this will be equal to theta 1 dot theta 2. Okay, so this way you can relate your end effector velocity. This is your eta, which is equal to. Now, if you look at this matrix, it's a function of theta 1. There is no theta 1 dot in this. This is a function. So we write this is a function of, I'm going to say this is a function of theta. Function of theta 1 and theta 2. Because you have theta 1, theta 2 here. Okay, so this will write it as j of q, because q is theta 1 and theta 2. And this will be equal to, this is a differential of theta times q dot. All right, so this is now, if you look at the expression, this is called the manipulator Jacobian. It's called the manipulator Jacobian matrix, and it is a n by n matrix. So it is J n by n. So if you have n by 6, I'm sorry, if you have 6 degrees of freedom, it will have 6 columns. So the number of columns in the matrix of J will be the number of degrees of freedom. Okay. Now, if you look at this expression, you'll notice that we have, why do I write this as J of Q? Because it's a function of theta 1 and theta 2. Q is theta 1, theta 2. So Q is nothing but theta 1, theta 2. Q dot is theta 1 dot and theta 2 dot. So if you have a position here like this, so let's say this is a point P in space. Now I have a 2 degree of freedom manipulator. We have studied this already. I can reach this point in two postures like this. I can reach this point like this, and I can reach it like this, right? So this is my elbow up position, this is my elbow down position. So let's say that the joint values here are Q1. The joint values required to reach this point and this posture is Q2. So if I find the Jacobian here, in this case, J of Q1 and J of Q2, will they be the same or different? Because what I'm trying to explain is, you're reaching the same point in space, right? You're reaching the same point because this has 2 solutions. If you go to a more complex manipulator, you will have 4 or 5 postures that you can reach the same point in. So in this case, this is one posture, okay? Q1 is one posture, Q2 is another posture. Now, if I calculate the Jacobian here, and if I find the Jacobian here, obviously, here I have to use these joint angles. And here I have to use these joint angles. Will J1, J of Q1, are these equal or different? Huh?
I think it's going to be different.
They will not be the same, okay? They will not be the same, because that's why these 2 Jacobians will not be the same, okay? They are different. The reason they are different is because the posture of the manipulator is different. Jacobian is a posture-dependent matrix. Jacobian is a posture-dependent matrix. That means you can be at the same point, but in a different posture, the Jacobian will be different, okay? So sometimes you'll have a choice. Should I go to this point in this posture, or should I go to this point in this posture? Which is better for me? That depends upon how well the Jacobian is. And we'll talk more about it as we study the properties of a Jacobian. What should be a Jacobian ideally be like, so that you're able to judge the posture of the manipulator. But for now, just remember one thing, that for the same point in 3D space, you can reach that with multiple postures. And at every posture, the Jacobian is different, because obviously it depends on theta. So here you have theta 1, theta 2, double dash. Here you have theta 1 dash and theta 2 dash. This posture is completely different from this posture. So obviously the Jacobians will be different. Okay? And we'll study the properties of the Jacobian.
Professor, the Jacobian matrix determines the velocity of the...
It's a mapping between, so when you write this, when you write eta is equals to J Q dot, or J of Q times Q dot, that means it's mapping end effector velocity into, it's mapping the joint velocity into end effector velocity, okay? So it transforms joint velocity into end effector velocity. Okay? So, because when you have a manipulator, when you're moving your hand, you're moving the joints, you're not, so, and that relates to moving the end effector eventually. So you want to know that if I'm moving the joints at a certain rate, how fast my end effector will move and in which direction. Okay? So this is the forward problem where you're moving this. Now there can be an inverse problem. I want to move in this direction at the velocity, given velocity. What should be my joint velocities? The inverse velocity problem is as follows. In this case, the forward problem is this. So for example, you have the forward problem, which is given the joint velocities, okay, find the end effector velocity. Okay, which is eta. Okay, joint velocities is q dot. Okay, this is your forward problem. The inverse problem is like this. Okay, the inverse is find the necessary joint velocities to generate given end effector velocity. Okay. So you are given eta, you need to find q dot. So how do we do that? We just take the inverse of the Jacobian here. We know that eta is equals to j of q times q dot. So we'll multiply this by inverse. Right? So this will be your identity matrix. So you can say q dot is equals to j inverse. Okay? So you can take the inverse. Obviously remember that eta times j of q is not equal to j of q times eta. Alright? So if we take the inverse of this matrix, let's take the inverse Jacobian of this. Let's take this matrix, let's take the inverse of this matrix. So here you have eta will be equal to a1 sine 1 minus a2 sine 1 2, a1 cos 1 plus a2 cos 1 2 minus a2 sine 1 2, a2 cos 1 2, eta 1 dot. Right? So j of q is this. J of q is equal to this matrix. So let's find j inverse of u. Right? So that will be determinant of j. So this will be equal to. Okay, so if you have a matrix A, which is equal to A, B, C, D, A inverse will be equal to right, a 4x4 matrix. So you can find A inverse like that. So in this case, we'll find this is nothing but the determinant of A, AD minus BC. So in this case, when we do this, we'll have A2 cos 1 2 and here we'll have minus B, so this will be A2 sine 1 2 and this will be minus C times here I'll have Okay, determinant of JQ will be AD minus BC, so we'll find J of Q will be equal to AD, we'll multiply these two. Minus BC, so minus of alright. So this is going to be equal to minus A1, A2, sine 1, sine 1, 2. I'm sorry, cos 1. Minus A2 square sine 1, 2, cos 1, 2. And this will be plus A1, A2, cos 1, sine 1, 2, plus A2 square cos 1, 2, sine 1, 2. So we'll be left with A1, A2, we'll write this as sine 1, 2, cos 1 minus sine 1, cos 1, 2. So this will be equal to A1, A2, sine 2. Okay? All right. So we can write J inverse of Q as 1 over A1, A2, sine theta 2 or sine 2. And here you will have the matrix So now we can find the inverse, which is to find Q dot, it will be equal to now as you can see that this is a simpler way to do it, only if the manipulator has a very analytical form of a forward kinematic equation, you differentiate this. Now you can see here that you have theta 1, theta 2. When I differentiate this, let's say you have 6 thetas. It becomes rather tedious to do this. So you need a more generalistic approach to developing a Jacobian. So what we'll do is we'll try to figure out a way where we can write the manipulator Jacobian by looking at its DH table. Alright, so we'll take a general approach to finding the manipulator Jacobian. Okay. Alright, so if you look at a Jacobian for an n degree of freedom manipulator, the Jacobian will have n columns. J of Q will be like this. J1, J2, up till Jn. Okay. Every column will be like this. Okay. One column for each joint of the manipulator. 1, 2, J3, J4, and so on up to Jn, like that. Now, when you look at eta for a fully non-redundant manipulator, eta will be like this. X dot, y dot, z dot, phi dot, theta dot, and psi dot, right? This will be end effector velocities. This is your linear velocity of the joint. We call this as v. Okay? This is the angular velocity at the rate at which the orientation of the end effector is changing, which is omega. Okay? So you can write the eta as v and omega. This is the rate at which the arm is moving. This is the rate at which it's turning. Okay? So the Jacobian has to compensate for that so that this is properly mapped. So every column of the Jacobian, Ji, can be written as Jv and J omega. Okay? Every column of the Jacobian will have Jv and J omega. So in other words, I can write J of Q as Jv1, J omega 1, Jv2, J omega 2, Jv3, J omega 3, and so on till Jvn, J omega n. Now, depending upon whether the ith joint, for example, somewhere in between here you will have Jvi and J omega I. Okay. So depending upon whether the joint is basically a revolute joint or a prismatic joint, we have to find out the Jacobian. And when we club them together, we have the complete Jacobian matrix. So this will be decided based on, we'll do a case-by-case example where we consider first joint to be prismatic and then the joint to be revolute, and then we'll put it together. Okay. So let's say that we have case 1 where the ith joint is prismatic. Okay. So ith joint is a prismatic joint. So let's take a example here. So we have a joint here. This is my base frame. This is Z naught, X naught, Y naught. Here I have a prismatic joint, which is the ith joint. This is my final ON. Okay. This is OI minus 1. All right, and this is O0. All right. Now this will be, because there is motion along this is Zi minus 1. Okay, Zi minus 1. This distance is OI. This is OI minus 1. Okay. So when this moves, this is a prismatic joint. Ith joint is a prismatic joint. This will be Di. It moves up and down. This is Di. Okay. Di is along Zi minus 1. Okay. So we are picking one joint within the n number of joints that the manipulator has, so that we can find the Jacobian at this. This is our prismatic joint. Okay. This is the joint which is prismatic. So when the joint moves, what is going to happen to ON? ON is the final wrist coordinates, right? There are always n plus 1 frames. We start from O0, we go up till ON, which is n plus 1. So when there is a displacement along Zi, what will happen to ON?
It's going to displace about Zi.
Absolutely, it's going to move about Zi. It's only going to move, either this is going to move up or down, right, by Di, whatever it is. Okay, so if you look at this, right, eta, let's call this eta as V and omega. When I move this, let's say that I'm moving this at a rate of D dot, this will also move at the same rate, right, because I'm raising up and down. Will there be any change in omega? No, there is no turning effect. So this will be, there is no change in omega. So in the case of a prismatic joint, j omega is equals to 0. Okay? J omega is equals to 0, or j omega I for the ith joint. If ith joint is prismatic, j omega I is equals to 0. Now we need to know what is jvi. The motion is along this axis by d dot. So jvi will be equal to zi minus 1. Okay? So for a prismatic joint, Jacobian ji, okay, for a prismatic joint, I'm just going to write it as P like this. For a prismatic joint will be equal to jvi, j omega I, which will be equal to, in this case, vi is zi minus 1, omega I plus 0. Alright? Obviously, when we multiply this by q dot, di dot gets multiplied because you're going to multiply the Jacobian with the rate of change of the joints, so that automatically gets multiplied when we construct the final form. Let's take the second case where this joint is a prismatic joint. Okay, so this is case 2. Case 2 is ith joint is revolute. Okay, this is a revolute joint. All right. So we have your first joint. Let's go to the ith joint here. We'll draw it as a prismatic joint like this. I'm sorry, the revolute joint like this. Okay. Now, in this case, let's again think about the same thing. Okay. We have J, I for a revolute joint R, which will consist of two parts. First is your JD I and J omega I. All right. Let's deal with omega first because it's intuitive.